Welcome to video 2 of the RA1 Prep. This video is going to focus more on the Tidyverse library, as we can see, and these topics right here. I will warn you that we're not going to cover anything, and also this might take a little bit longer than video 1 because I want to do more examples, especially with ggplot and dplyr, because these are things you're going to need to know in RA1, and I don't want to just brush over them. So, in video 1, we ended up making a CSV that looked something like this, where this is simulating data from Synchro, where we have a particular intersection, the date it was produced, the report, let's say, the ID of the intersection, the timing plan ID, so AM, PM, or midday, the name of the timing plan, and then the splits for the 8 phases, the cycle length, and then the offset from the master controller. And so right now you can see that all of my data is filled in, there's no missing data, and everything's delimited with commas properly. And if we were to put this into R, it would come in as a data frame, like we'd expect. But I want to see what would happen if I left some values blank. And also, I put in this data type because if you'll remember from our last video, that's not a standard date format. So I just want to see what will happen when we import that. But now, let's leave some values blank and see what will happen when we import this. So the file is called signal CSV. I'm going to go save as, and I'm going to move it somewhere that's convenient for me. Let's say to my documents, semester 6, and I'll go into stats, and let's make a new folder, call it test, for example, whatever. And we'll put it here. So going back to our studio here, if we have a look, refresh here, we should see the folder called test, and there's the file right there. If we want to actually pull it into R, import it, we're going to use a library called readr. readr. And readr is part of the Tidyverse, and specifically from readr, we're going to be using the read_CSV function, like that. The reason for that is this function will automatically deal with header rows, so the names of our columns in our data frame. And it has a lot of nice arguments we can set, and it'll give us an output that I think will be a little bit different than you might expect. But in general, it'll handle things pretty nicely for us. And the only really argument that we need to provide for now is just the path to the CSV file that we want to open. The easiest way to do this in RStudio, if you'll recall from our first set of videos, is via an RStudio project. So recall that in RStudio project, we can create them and they have an rproj extension, so .rproj. And what they are is essentially a way of collecting or keeping all our files organized in one place. That's one use case. But more importantly for us, an RStudio project gives us a relative directory structure. So what that means is that file paths will be relative to the folder containing the R project file. So what I mean by that is if, for example, this is the folder that has the R project file and it's at some path sem6 stats. If we made another folder, like into data, but our project file was located here, then this data would be relative to this path here. And the main advantage of that is we can use shorter file names because it's relative to an existing path, but also if we were to copy that folder or share it with somebody else and they were to copy our project folder that has our R project file, and they didn't delete the R project file, they didn't delete any folders, that path will still work because it's relative to that folder, no matter where they place it on their computer. So let me show you how we do this again. We go to File, New Project, or you go up here the project, but we'll go here, File, New Project. We won't save here. It's going to open up a new window in a second here. And it's going to ask us whether we want to use a new directory or an existing one. I'll use a new one to create a new working directory. We're going to select New Project from the list here. We have a lot of options. And here, where do we want it to be a subdirectory of? So meaning what folder do we want this to go inside of, essentially? And what is the name of this new folder? So let's call this Tidyverse Prep. And I want to check this to open the project in a new session and hit Create Project. And you'll notice, I'll do this here. You'll notice eventually what'll happen is we'll get a new session of RStudio. See, it's opening right in the background now. So a new instance of RStudio that is going to be specific to our project that we just created. See that we have the project name up there, Tidyverse Prep. Our working directory is now set to this. We can actually use getwd, get working directory, to see that's our working directory. And now any other path that we make will be relative to this. So, for example, I'm going to make a new folder and I'm going to call it data. And inside of data, let's say I want to put in that signals file. So let me grab that file from my desktop and go to stats. And in this case, we named it Tidyverse Prep data. Paste that in there. So there we are. We have inside data folder, signal CSV. Now, if we want to refer to that file, we just do this. data/signals.csv. So that's very easy. We don't have to type in C, users, my name, documents, sem6. We can just type this. And also, this will always be relative to this structure. So as long as you have this folder anywhere in your system, it'll know to look in data and find this file no matter where. So with that said, let's actually go into reading it. So first thing we need to do is load in Tidyverse. So this is a library, so we use the library function. And I'm using this in the console right now, but really I should be doing this in the script editor. You'll see that we get a bunch of what they call core Tidyverse packages. We'll see we get dplyr, ggplot, lubridate from earlier, and readr. And we get some conflicts between existing functions, but that's not a huge deal. More importantly, now we have access to each one of these and we can use the functions that they have within them. So Control L to clear our console. Go File, New File, RScript. And here, to read in our CSV, we'll just do this. We'll say this is signals data, so we'll call it signals df. And we're going to assign this with binding it with the assignment operator to read underscore CSV. Underscore means that we're using a readr function. And then the path to that file. So data, and I use tab to complete it. And if we just run this with Control Enter, you'll see that it loads in and it gives us a preview. And you'll see that it's available here. And if I click on this button, I'll get a view of it. And here's our data with all our different columns that are column vectors that correspond to variables and rows that correspond to observations or attributes for those variables. And you'll notice NAs here because those correspond to the missing values. Our defaults, as I mentioned before, when we doesn't know what to do and there's something missing, it just defaults to NA. And that means that we have less data available to us. So you can think about why this might occur. Let's say Synchro spits out an empty cell here instead of 0. That could be one case where that could happen. Now, I want to show you though, if I run class on this to get the type, you're expecting data frame. Let's see what it is. Spec TBLDF, TBLDF, TBL data frame. Well, that's not exactly a data frame. So what's going on here? Well, when we use readr, which is part of the Tidyverse, we get something called a tibble, or a tidy data frame. And you can think of this as basically Tidyverse's version of a data frame, which includes a lot of modern convenience features. And I want to actually compare what are the differences between a tibble and a data frame. Well, let's have a look. If I print out this tibble, look what I get. First, I get the type of data and the dimensions right away just by printing it. I don't have to run structure on it. I can see it's a tibble. I can see the number of observations is 3, which I see here. And the number of columns or variables is 14. We have 14 columns, which means the overall dimensions are 3 times 14. We also see that doesn't change the input type, right? For example, date produced here, you think it might convert it into a date type or a factor, but it just leaves it as a character, the way that we've written it. The other thing you'll notice is we have a space in date produced, but it leaves it alone. It doesn't try to get rid of the space or do something to get rid of it. So it doesn't change the names of our variables. And you can see also that it shows the type of each column below the name of the column. So for example, location name, CHR for character. Intersection ID, DBL for double. S1, DBL for double. Plan type, CHR for character. And it shows NAs for not available values. The other thing, and this is not super obvious right now, is if we had more data, a tibble would only show us the first 10 rows compared to the data frame. So just to show you the difference, I'm going to pull in an existing data frame that comes with are called empty cars. So compare this, empty cars. See, when I run that, I just get everything out. I do not get the dimensions by default. I do not get the types by default. And I get a lot of rows by default. And I don't get even row numbers here. So that's the difference. But we can use both of them pretty much interchangeably. Our preference is to work with tibbles because they are built for Tidyverse. Now, we also noticed one thing. Maybe you didn't notice it right away, but if we run signals df again, date produced as a character. It's not a date. And the reason is we're providing this in a format that's not standardized. Remember that we use ISO 8601, which defines dates like this. And we're not providing our date like that, so R doesn't know how to process it, so it just leaves it as a character. It doesn't try to change it. We can actually change that behavior if we want on import by passing another argument to read_CSV. And the argument specifically is call_types. This lets us manually specify the column types. And we combine this with column date and format codes to convert this character of date produced to an actual date. So let me show you what I mean, because it's a little bit, seems a bit hard to explain right away. I'll move it to a new line just to make it easier to read. And so I'll do here, column types, and R loves auto-completing for me. RStudio loves auto-completing, which is nice. And here, we use the columns function to access the different columns. And then we specify the column that we want to change. So it's date produced. And then we put in equals column_date. And here we put in a format for the date. So the format, we have month, then day, then year. And so we'll put in a format code here. And if this all seems weird to you, refer to the first video. It's not super critical. But we have the month name, then the day number, and then the year. So we have month, day, then year. So the format code we would specify is, the format code we're going to use is %v space %dth comma %y. And if we run this, we get an issue. And let's have a look what that issue might be. Let's look at signals df. We get an issue NAs, so that means we did something wrong with our format code. So I'm just going to double check it, pause the video real quick. And the issue here is this th here. It doesn't really handle dates like January 9th. It just does January 9, right? But there is a solution, which is arguably easier. We read in the data as normal. We look at it, and then we use lubridate. So we do something like this. Date produced is, and then this is month, day, year, so MDY, signals DF, date produced. And this should fix the issue. And if we look at signals DF, there we are. Month, year, 4-digit number, dash, month, dash, day. All corrected nice. So that's an application of something I did in the last video. It's not super important. The next question I want to talk about is why bother with tibbles? You know, why not use just plain data frames? And there's a couple reasons. First, as we've seen, tibbles are more user-friendly than data frames. They give us convenient features like handling column names for us on import by default, not explicitly or implicitly converting data types without us knowing, showing a preview of data types for us without us having to use structure. So just a lot of convenience to it. Also, when something goes wrong, as we saw earlier, it will give us something that looks like this, some detailed information, which makes it easier for us to troubleshoot. It gives us more detailed error messages. Also, tibbles are designed to work with other Tidyverse functions, making data manipulation and visualization, as we'll see later on, more consistent and easier to approach. And the third point, something that is you might see, some things that we can do in base R are very tedious and they're much more streamlined in Tidyverse. Tidyverse lets us quickly do stuff like filtering data, combining data, applying functions to specific columns, subsetting it, much more, where that might be very hard to do in base R or require a structure that is necessarily limiting. And maybe, to show you an example, Tidyverse functions tend to be very intuitive in how they're written, and they are closer to natural English language, which makes it a little bit easier to understand what they do and how to learn them. Let me show you what I mean. A function in base R for grouping is called aggregate. That might not be obvious to you what that means. An equivalent function in dplyr, in the Tidyverse, for grouping is group by. Even if I don't know anything about these functions, I have a better idea what this one does. It's grouping by something. This is not super clear how to use it. And that's exactly why we are using Tidyverse, one of the features, one of the reasons. And the final thing is it gives us a pipe operator, and we'll cover that a little bit later. Now, when we work with data, the entire process of working with data, meaning, importing it, and then cleaning it, and then transforming it, visualizing it, modeling, and finally presenting. When we go through that process, we have libraries in the Tidyverse that are designed to support each stage of that process, which is another reason for using it. For example, at the importing stage, We have libraries like the ones we've seen already, readr, but we also have stuff like Google Sheets 4 and rvest and httr. These are to get data from different sources, Google Sheets or an online source, things like that. For tidying and transforming, we have libraries like dplyr, tidyr, lubridate, and purr. We've worked with lubridate, and we're going to work with dplyr later on. For visualization, the main library that we have is ggplot2. And then for modeling, our main libraries are things like broom, infer, and fable. I'm going to focus on importing with readr, which it's already done. But I want to do another example just to show you. Then I want to focus on transforming data with dplyr. And finally, visualizing data with ggplot2. That's going to be their main focus of this video. So let's go back to our data that we imported, and we can see we have NAs. And we could worry later on how to fix them, how to avoid them, things like that. But I just want to show you what would happen with missing data. I want to use something a little bit more complicated just to show you how that might work. And I want to use an external data set. Specifically, I'm going to use a data set of direct marketing campaigns that originate from a Portuguese bank. And this data comes from UC Irvine's Machine Learning Repository. And I've provided a link in the description if you want to download and follow along with me. So let's read in this data and explore it. And if we try read CSV, you'll immediately notice some weird behaviors. Let me show you what I mean by that. So, importing. The data that I'm talking about, in this case, is available in this folder, here, here, and that folder right there. So let's actually go back to here and open up this R project file. I've set it up already just to make things easier for us. And when we open up this R project file, the reason I'm doing it is because I can easily read in the file. Easily read in the file that I want to use. So here we have a data folder. Inside of that, we have the file we want to use, bank full. So bank tibble read CSV data bank full. Now, this doesn't work because, of course, I did not load in Tidyverse. That's something we always have to do. Once that's loaded, this will work. Perfect. Clear the console. And we'll run this again. Now we have 45,000 rows and one column. And so let's have a look at this. What's going on here? That doesn't look right. We have a bunch of semicolon separated things, and it's coming in completely wrong. So what's going on here? Why are we getting this output? Well, let's have a look at this data actually to show you what's going on. So I'm going to go to that location and I'm going to look at this data set in Excel. We can use it in Notepad, but whatever, Excel works. And just have a look at how this is structured. The columns are separated by a semicolon. They're delimited by a semicolon, not a comma. So that's our issue. We're using the wrong delimiter. We're assuming it's a comma, but it's not. But then what's the solution? How do we handle that? Well, this is where read CSV2 comes in. Read CSV2 is another importing function that uses the semicolon character, this character, as the delimiter. And if we do that, this should be all fixed. So read CSV2, run this again. 45,000 rows, but now 17 columns. That sounds more reasonable. And let's have a look. That looks correct. And that looks how it should. So now we've learned that there's a different way of importing depending on the delimiter that we have. Now, let's say I want to know all unique values for the column vector of job, which is a character right now. For example, we see a management, technician, entrepreneur, blue collar, unknown, retired. What are all the unique values? There's two ways we can do this. The first is a review from our last video. Coerce it into a factor. So what I mean by that is coerce it into a factor and use the levels function. Levels function will give us back the named levels of a factor. And remember that levels in a factor represent the unique values that categorical variable can take on. So what I mean is this. Levels factor bank tibble job. These are all the different levels that that factor takes on. So all the different possible values of that categorical variable. But I think this is a little bit confusing. You have to access this, then you have to wrap it in factor, and you have to wrap it in levels. Seems not the most intuitive or easy thing to understand. A better approach is the unique function. And this function will return unique values from a vector as a vector, removing any duplicates. So let me show you. We call unique, and then we just pass in a vector. So in this case, I'm using the $sign because these refer to the names of these columns. Like $sign job is this. And this will give me back the exact same output. Or it should, oh, yeah. Not DF, it's bank tibble. And there we are, exact same output. Use whatever one you like, but I prefer this one because I think it's a little bit easier. And we'll see later on that there are better ways of doing this. So that's one thing we can do. The other thing, if we look at our tibble again, is you'll see that day and month are in separate columns. Day is in one column, the date of the transaction, the day of the month, and month is a separate column. And because of that, R is treating day as a double and month as a character when we know it should be a date, right? And we know it should be combined. And we can imagine that we might want to make a new column in our data frame that combines these two, day and month, right here, into a single value, and then use lubridate to convert that into a standard ISO 8601 date format. There's lots of ways we can do this. But this is an excellent use case for dplyr, and it's our segue into covering dplyr. So let me clear the console for now. I'll leave this in memory because we can use it later on in our discussion of dplyr. So dplyr, you might even say dplyr. I sometimes say that wrong too. But what is this? I'll write down a definition. It's a library for wrangling, which is a fancy way of saying managing, data, and it's loaded as part of the Tidyverse, as we saw earlier, right? If you did a library Tidyverse, you'd see dplyr. So it's a tool that we use for data management, for tidying, and for manipulation. And there's a lot of things you can do with that, obviously, but these are the topics I want to cover. Pipe operator. glimpse function. The filter function and the select function. The rename function, or renaming, I should say, and arrange function. The mutate function and the group by function that I mentioned earlier. And then the summarize and count functions. These are the topics I want to cover in relation to dplyr. So let's start with the pipe operator, which is arguably one of the most powerful things that Tidyverse exposes to us. So the pipe operator, you'll write it like this: %write%. And what that is, what that symbol means, is equivalent to the English word then. Because what a pipe tells Tidyverse, or what a pipe tells R to do, is do one thing, then do another. So this is a functionally equivalent to thinking about the word then. So think of the word then to understand what they mean. So what am I referring to here? Practically, what I'm saying there is that it lets us combine many functions together in some specific order. So I want you to picture this. A is a data frame. B, C, and D are functions of some kind. It doesn't really necessarily matter, but let's say they're dplyr functions. The way we would use a pipe operator is like this. A, pipe into B, pipe into C, pipe into D. And what that means is, starting at the data frame A, take it and put it into function B. Run function B. That'll give us some output. Take the output of that function B and put it into function C. That'll do something else, give us a different output. And then take that output and put it into function D to do something else and get a final output. So, all that to say, the output of one step becomes the input of another step. And I want to be specific here. Specifically, by default, the pipe operator will pipe some value to be the first argument of a function. And we can use a very silly example just to illustrate how this works. And by the way, you might see this more often. Reason being, this is more readable because it means like a waterfall, do that, then that, then that, then that. So when I say it pipes a value to be the first argument of a function, let's create a simple function. We'll call it adder. Adder is a function that'll take two values, A and B. And all adder will do is give us A plus B. Very, very straightforward, base R, nothing tidyverse about it. So as an example, 2 and 6 gives us 8, because 2 plus 6 is 8. Okay. So let's say I use the pipe operator along with my adder function, because that's something we can do with tidyverse. We can use the pipe with non-tidyverse functions. So if it becomes the first argument of my function, that means it'll become the A value. And I want to show you this. 5 pipe adder. What do you think will happen when I run that? What do you predict will happen? Let's run it and see. Argument B is missing with no default. So argument B is missing, which means it got argument A. And that means what the pipe has done is taken the value 5 and piped it to be A. And just to drive home the point, let's say 5 plus 10 is 15, right? So if I put in 10 here, and run this again, I get 15. And why is that? Well, what this is doing is a functionally equivalent to doing this. We're taking the value to the left of the pipe and we're putting it into the first argument of our function here, which does this. And then this value 10 is the second argument of the function, and that's why we get 5 plus 10, or 15, as our result. So that's how we use the pipe, or one basic use case of the pipe. We'll use it quite a bit throughout dplyr, so you'll get quite familiar with it. When we're working with data, we can use a function called glimpse to get a preview, a glimpse of the data, but in a wider format rather than in a column format, in a more of a row format. So as an example, glimpse bank tibble. Let's have a look at what this does. See how we get everything in a more like a row format? We get the number of rows, we get the number of columns, we get a listing of all the columns, and we get a $sign, meaning we use their name to index them. We get their type, and now we get a much more of a detailed look into the different values they might take. So we can see, oh, for P days, we're looking at mostly -1s, and for month, it looks like it's all May, and for day, it looks like it's all 5. So maybe a lot of these transactions happen on the same day, and that's kind of how we should use glimpse. Now let's get into some more dplyr heavy things, and let's go into filtering. So filtering lets us use a condition to get back a certain subset of our tibble. So let me motivate this with an example. Suppose we're only interested in the survey results for people who are married, meaning people for which marital status is married. So I don't want single and I don't want divorced, for example. We can actually very quickly run unique bank tibble marital just to see the values. So we have married, single, divorced, and I only want married, right? To do this, we use dplyr's filter function, which I mentioned will output a new tibble that meets a row-by-row condition applied to the original tibble. And the way that we write it is filter some data and then a condition. And let's practice pipes because the first argument is data, so we can pipe in the data. So, for example, bank tibble, pipe into filter. It will become the argument data, and then here we can specify a condition. And in this case, since we're using data, since data is defined, we don't have to prepend it with a $sign because dplyr knows it's in reference to bank tibble. So what that means is I can just use the word marital. So I can say where marital is married. And well, it helps if you spell things right. So marital, and run it again. And now you see we have a new tibble. It has less rows than original one, which makes sense because we've applied a condition, and so we should expect there to be less values that meet that specific condition than all values. In fact, we have 27,000 rows that meet that condition versus 45,200. And we can see, if we look at marital, married, 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 all the way through. So I want to be clear here what is going on. So we are piping the bank tibble using the pipe operator. We're piping that into the filter function. It'll become the argument of data. So effectively, we're just doing this, but in a more concise way. Then we provide a filtering condition, that being that the column marital is double equal comparison equal to the character married. And that function will retain all the rows which satisfy the condition in the original bank tibble and remove those that don't. It's not really removing, but it's just giving us a different data frame or tibble that has all the rows that satisfy the condition, which subsets the tibble and gives us a smaller tibble back, or a smaller data frame back. And because this outputs a data frame, we can do something like this: married only, and assign it. And now married only is this smaller tibble that has marital status only to married. And so that might be something, if we want to just look at that particular group of people, that's one way of doing it. And because filter is working on rows, our columns are unchanged, so we get the same columns back. We still get 17 columns back with no changes to them. We can also do multiple conditions. So we can do, for example, marital status and their bank balance. And I want to show you, by the way, let's say you don't like the pipe. You can do this. Marital. This is going to be the exact same thing, right? The reason I'm using the pipe is just because it makes it more concise, and I also want you to have practice with it. So now let's try multi-condition. Multi-condition filtering. So this condition that I'm going to use here is this. Let's say that they are married and their bank balance is greater or equal to 10,000. And in this case, this is in Portugal, so let's say it's euros. So the way we do this is like this. And I'm going to clear the console because it's getting a little bit crowded. Bank tibble. Pipe that into filter like before. But now we're going to put in two conditions. And remember, when we want to do two conditions, for example, with logical indexing, we use the AND to combine for combining two conditions where both have to be true, or the OR, where either of them is true. Same thing applies here. So marital equals married and balance greater than equal to 10,000 euro. And now we get a way smaller tibble, 543 rows, but now look, every marital value here is married, and all the balances here are at least 10,000 or more. And so that's how we can use filter to get out data that we want. But you're getting all the columns. What if I just want specific columns? For that, we need a different function. Select to get specific columns. Filtering row by row condition, just so you know. So select, let's call this Tidyverse testing. Save the script. It's just kind of a good idea to do that. Select will accept the names of columns that we want to keep as arguments, and only those columns will be kept, and they will be kept in the order that we specify. So simple case right now. Let's say I want to get a tibble that's the same number of observations as the original one, but I only want their age, their job, and their balance. So the way we do that is like this. Bank tibble. But now instead of piping into filter, we pipe it into select. And the columns that I want to keep, remember, are age, job, and balance. Look at that. Now we have a tibble that has 45,000 rows, but only 3 columns: age, job, and balance. And so if that's all I care about, I can just extract that. And we can, of course, combine this with filter to do both things at the same time. And I want to show you, by the way, if we didn't have the pipe and I wanted to do filter and select, what I'd have to do is this: select, filter, and then put in a bunch of stuff. I think that's hard to read and hard to understand. With a pipe, I just do this. Data, pipe, filter, condition, pipe, select. I think this is more intuitive and it follows the flow of the logic that we're using. So that's one simple use case, but I want to show you that the order matters. So right now we've put the order as age, job, balance, but what happens if I do this? Select, balance, age, job. What do you think will happen here? Will you get the same output? Let's run it and find out. Balance is the first column, then age, then job. So we can reorder columns by just passing them into a different order into select. And so in another way of saying that, the output of select is reordered to match the order specified within the selection argument, the arguments in the function. And one final thing that I'll show you with select that I think you'll find useful is we can use select to rename columns. So the way we do this is we select the column and then we just do something like this. We use new name equals old name, where old name is already defined in the data and the new name is the name we want to use in favor of it. So as in the example, going back to bank tibble, and let me view it in a separate window here. Run this. So for example here, let's say there's a column called contact, and that's the method that we use to get their contact information. Believe its values are unknown, telephone, and cell. We can actually check that with unique bank tibble contact. Yeah, unknown cellular telephone. So contact maybe is not the best name for it. So what if I just do something like this? Bank tibble. And now I'm going to select, and we'll put in a new name here. So for example, contact method equals contact. And if we run that, see, now I get a header of contact method instead of contact. And so we've renamed the column just by doing that. So let's talk now about ordering things. And that's the job of the arrange function for ordering stuff. So let's say I want to sort the particular rows of my table in ascending order by some specific column. So good example for that might be balance, right? If I have a look at bank tibble, right, our balances are all over the place, right? I have one person with 2,000 euros and 29, then 2, then 1,500, then 1. There's no real order to it. I maybe want to do it in ascending order where I put the person who has the lowest balance first and then the person who has the highest at the end. And the way we do that is, of course, with the arrange function. And this function has the signature like this: arrange, and simply the data that we want to use, which you can pipe in, and then the column to arrange. And by default, this will arrange in ascending order, so smallest to largest. Let's try this with our bank data here. So bank tibble, arrange, balance. Run that, and wow, see that we have someone with negative 8,000, and every row we're getting more and more positive, right? And even now I want to reassign this because I want to look at something. If we look at this and then we have a look at the values of balance, see how it's coming in order here from negative 8,000 and then getting increasingly more positive. all the way to negative 406 and beyond. So that's how we can arrange that way. And let's say that I don't want to do an ascending. Let's say I want to do it in descending order. So this is ascending order. If I want to do it in descending order, all I have to do there is call in the descending function DESC and combine that with a range. Works a very similar way. We use a range, but then we pass in DESC and then we put in the column that we want to sort our rows by, but this time descending. So again, let's do balance. So arrange descending balance. And now we see the highest balance first, 102,000 euros, then 98,000, then 81,000, then 81,000, then 71,000, then 66,000, then 64,000, and so on. And so that's how we can do arrangements. The next thing is mutating, which is a fancy way of saying new columns. So comment this out. Mutating, or the mutate function, mutate lets us make new columns. And why would we do this? Well, typically we do it to make new columns from existing ones, usually to apply some sort of transformation. So as an example, maybe balance right now could be in just dollar amounts, but maybe I want to divide that by a number to express something, or maybe I want to divide it by, multiply it by something, or to express some sort of thing, or maybe the age, I want to do something stupid like double it. We can do that and retain the original column. And all that to say, mutate will add new columns, one or multiple, while preserving the original tibble structure. So what does that really mean? That means if I run mutate on something, it will give me a temporary tibble, but it won't overwrite my original one. And so that's good, because then we can do what we want for that particular type of analysis and not change the underlying structure, which might mess up our data and cause us to have to redo everything. And the argument, the way that we work with mutate is like this. Mutate new column name equals expression. And expression here can be legitimately any valid R expression, right? So it could be math related. Could say something like this. So it could be a math expression. It could say, hey, double duration is duration times 2, and that's just taking this value multiplied by 2. So 90 to 180, or 45 to 90, and things like that. It could be also function related. So we could say something like maybe logarithm balance is log 10 balance. So we're applying a function to an existing column to get a new column. That's the result of applying that function. It could even be something stupid like a character, right? Which is something we won't do terribly too often, but maybe you could say something like is old. And then we could do like a conditional. Right, we do if else age is greater than 65, old, not old, something like that maybe. And we can even refer to other columns like we've seen here. All right, we refer to duration, we refer to balance. Now, I want to do something a little bit silly, but just to show you how this might work. I'm going to, for example, look at default, right? Default, I believe, has values of no or yes, right? Have they defaulted or have they not defaulted? Again, unique, bank tibble, default. Yeah, yes or no. Which, by the way, that should be a factor, but whatever, I won't worry about that right now. So have they defaulted or not? Well, let's make a new column that does something stupid, but just to show you the point. So we'll put in a tibble. We'll pipe it into mutate. Now, the first argument of mutate is the data, but since we're piping it in, it's going to be bank tibble. Again, like filter, like select, like filter, this is equivalent to doing this. Bank tibble, and then the rest of our arguments. So now that our data is provided, let's do something like this. Broke. And then we do an if else. Default equals yes. Then they're broke. Otherwise, they're rich. So let's see if that works. See how we get a new column here called broke, right? But also, if I were to print out bank tibble, it's no longer there. That's what I mean where it doesn't modify it preserves the structure. It doesn't modify the original tibble. So if I wanted to see this, I can assign it to something like new bank temporarily. And then if we have a look at new bank, it might not show up, but remember we can use glimpse, take advantage of the width. And if I run glimpse of that, well, there we go. I got a new column broke. They're broke, they're broke, they're rich. That's a stupid example, but that's how we might do it. Here's something that's arguably a little bit more useful. So we have our balance, right? And it's a numeric value that could be negative. So let's say I want to say, is someone able to take a loan or not? Right. So I can do a condition similar to the way I've done it here, where I can say loanable is bank tibble. And the reason this works, by the way, is this returns a tibble. So we just assign it, binding it with the assignment operator to that new name. So bank tibble mutate loanable if else balance greater than or equal to 0. Yes. No. And if I run that, I believe I probably made an issue with how I've called. Yeah. Done that wrong, I believe. Yes. Seem to have an issue with my code here. So let's maybe troubleshoot this. There. That was probably the issue. That I didn't close my brackets properly. Unexpected symbol. And why might that be? Let me pause very quickly and check this. It was just a missing bracket. That's all I was complaining about. But if we have a look now at our new tibble, might not see it right away. It's because we have a lot of columns, but we can see loanable is now a new column here. And again, glimpse is very good for this. Also, structure is another good one that we can use for this. But here we go, loanable. Character type, no, so on. And the reason these are all no is because the balances are negative. And so that's how we can use mutate. Now, I want to talk about that problem I mentioned earlier, where we wanted to combine day and month to make a new column. And let's say we're going to assume the year is 2024, for example. We can use mutate to combine this. So here's our exercise problem. I will do this collaboratively. Combine month day, year, assume year is 2024, use luberdate. So what I'm saying here is this. I want to combine these two columns, month and day. So for example, July 7th, July 21st, May 29th, whatever. I want to combine them with the year because I want to get an output like this, 2024 01 10 or 2024 03 17 and so on, an actual proper date. So how should we do that? Well, the first thing that we need to talk about is a base R function that I didn't cover before called paste. And paste is a function in base R that lets us combine text or columns or vectors or whatever. So as a simple example, if I had a vector of months by name, Jan, Feb, Mar, April, May, June, whatever. And then I had days, and this is, I don't know, 13th, 14th, 4th, 1st, 19th, and 25th. So if I look at this month and days, that's just two vectors, one numerical, one character. I can do something like this. I can say paste, and then I can combine them. So I can say paste month days. Jan 13, February 14th, March 4th, April 1st, May 19th, June 25th. And you can see by default, the separator is a space, right? I can actually specify separator as something else like a hyphen, and then I get this. Jan 13th, February 14th, March 4th, April 1st, May 19th, June 25th. So the reason this works is because R is vectorized. It's going to do element by element, Jan 13th, Feb 14th, March 4th, and do this pasting. So if this works on character numeric vectors, then there's no reason it shouldn't work with the vectors in our data frame or our tibble. So that's exactly the approach we're going to take when we're mutating. And this is going to be our expression, right? Now, I want to show you if we assume something like, let's go back to this, and let's go year. And it's going to repeat, let's say 6 times. I believe this works. Yeah. So now we can do paste year, month, day. And there we go. 2024, January 13th, 2024, February 14th, 2024, March 4th, 2024, April 1st, and so on. And then these are dates we can handle with luberdate. So that's kind of the process we're going to follow here. By the way, REP stands for repeat. So I provided a value I want to repeat, and then the times I want to repeat it. And you can see that I get 6 repetitions of 2024 to form a numeric vector. So going back to this problem, I want to look at my tibble again. And we have day and month, right? So I'll do this. Bank tibble mutate date chr equals paste. I said assume 2024. So assume 2024. Then we're going to paste in the month and the day. Month, day, separator, this. And then now, let's say bank with date chr. Run that. And if we go glimpse, bank with date chr, or even view, here we have our date character, 2024 July 7th, 2024 July 21st, 2024 May 18th, and so on. And then now, what we can do is simple, is we can convert that into a date. So let's use something. Let's apply select. So type that into select and get date chr. And so now we get call date, let's say. And then column date, if you look at it, it's a tibble with just a date character. And then now I can say column date, date character. We have luberdate loaded because of Tidyverse. And our format is year, month, day. So YMD call date, date character. And then now if I look at call date, now it's all standardized. 2024-07-07, 2024-07-21, 2024-05-18. And so that's a nice way of combining a lot of what we learned here. We've combined mutate and select and luberdate, paste to create something very handy. So feel free to play around with this because there's a lot you can do. But now I'm going to move on to grouping data, which is just pretty, I guess, straightforward by the sound of the title. But what's the motivation here? Well, often we're interested in summarizing some information, some statistic within groups. So, for example, we might think average weight of men versus women in a experiment. Or we might think sales, max sales per region for a beauty shop. But either way, what I'm saying is we want to have a statistic to compare two groups to show the difference between those groups. That's something that we often find ourselves doing. And to do that, we have to group our data, which what that means essentially is segmenting it by specific variables. So we segment the data by specific variables. And typically, in this case, we use categorical variables because they have a finite number of categories that we can split and look at the relationships between those categories to do a comparison between them. The dplyr function for this is, unsurprisingly, group underscore by. This function will take as an argument the variable or variables we want to group by. So group by var1, for example, and we could have var2 and so on, but the easiest case is to just do one variable to group on. And like I said, var1 is typically categorical. Gender is a good one. Region is a good one. Think of it like this region example. We're grouping by region for sales data, and then we can calculate average sales per region to find the best and worst performing ones so that we can, chastise our employees. Now, when we do grouping, and I'll do it right now, it won't look like we did much. And really, the only real difference that we'll see is that we have a designation called groups. So let's look at our bank tibble again. I'm going to clear my environment. It's getting kind of full. And I'll go back up to the top here and rerun this to bring in our data cleaned as usual. And so now let's have a look at our data again. Bank tibble, glimpse it. And so here's our data that we have again. And now we might think, what do we want to group on? And maybe you want to group on education, right? Maybe you want to see, is the average balance or the minimum balance or the maximum balance have any sort of relationship to the educational attainment of the person? So whether they finished something unknown or elementary or secondary or tertiary, which is higher education. So to do that, very simple. All we would do is write this. we would say group by, and again, we provide the data in the group. So bank Tibble, and then the group, in this case, again, was education, right? Now, have a look at this. Doesn't look any different except for this. Groups education square bracket 4. 4 means we have 4 unique values for groups. And we can actually verify that by running unique bank Tibble education. And so we have 4 unique values for education, which is why we have 4 groups for that categorical variable. You can think of it, if you're familiar with factors, with the same idea of levels, right? And what we tend to do is we tend to combine the grouping with the function called summarize. So summarize, which does summary statistics. And what that function will do is it'll take a bunch of values. So it takes many values and aggregates them, which is a really fancy way of saying it combines them to get a statistic. And specifically, some of the statistics we can get are mean for average, minimum, maximum, standard deviation, count, pretty much any sort of descriptive statistic you might want to get from this. Quartiles, for example. Now, I want to do an example with it on a non-group data set and a grouped one, just to show you what summarize does in isolation, and then we can explain why it's used with a group. So for this, I'm going to use a data set that comes built in with R called CO2. CO2, if we run again data to see the built-in data sets, CO2 shows the carbon dioxide uptake in different grass plants. I don't have a clue about grass plants, but we'll work with that just to show you. And because it's built into R, we can just use it. So head CO2. Remember, head for data frames, you get the first few rows. So we get that. We can even run structure on it just to investigate what it looks like. It is, in fact, an NFN grouped data and data frame. Okay, cool. So just to make sure it's we can actually convert this to a Tibble if we want. We can do something like this: CO2 Tibble. And remember the as family of functions? So we go as Tibble CO2. And as Tibble is deprecated. Actually, I think it's as underscore Tibble, if I remember right. And it's CO2, not C02. Yeah, there we go. And so now, if we made it a Tibble, you'll see that it'll print out nicer and give us a nice, just better output in general, right? We get only 10 rows, we get our columns and our types. We see we have an ordinal, we won't worry too much about. 2 factors, 2 doubles. So let's say that I wanted to do something like find the mean uptake in this data set. How might I do that using the summarize function? Let me pause quickly. Coming back to it, I forgot to mention the summarize signatures, or the way that we write the function is summarize the data and then the name of the new column, and that's the statistic that we want. So if we want sum, we put sum. If we want mean, we put mean, so on. So when we don't group it, summarize is kind of useless, as we'll see right here. Let's say that I want to just look at the total growth. So it's going to be sum uptake. And if we look at that, total growth is a new column, and the sum is 2286. And if we go back to this, all that is done is it's added this column altogether. Not terribly useful because it doesn't tell me, distinguish really anything. But now, suppose I were to group on the treatment, which is a factor, so it has defined levels, it's categorical. If I were to group on the factor, summarize will look different. And we'll see that very shortly. So the way we do it is this. We're going to use pipe. We're going to pipe into group by, because group by, remember, wants data as our first argument. And so we'll do this. We'll do CO2 tibble, pipe into group by, and we'll group by, again, in this case, uppercase treatment. And then we'll pipe that output of group by into summarize. And in this case, we'll go uptake by treatment, and we'll do sum uptake. And have a look at what this is going to run out, what this is going to produce. We get a 2x2 tibble where we have our two values for our groups, non-chilled and chilled, and then we have our new summary statistics, a sum for each one of those groups. So we can see there's 1287 non-chilled ones and 999 chilled ones. So now we've discovered something that wasn't immediately obvious. So what's happening here? To clarify, when we are applying summarize to some grouped data, the calculations are made for each group. So in this case, we have two groups. So we have two summary statistics, two sums. And that lets us compare. We can say, there's more non-chilled plants than chilled plants. We can even do something like this. We can do, we can copy this and just change, instead of doing this, we can do average concentration by treatment. And now instead of doing a sum, we'll take a mean. And if we look at that, now we see the average concentration from the concentration column for non-chilled is a little bit higher than chilled. So we can see that ones that are not chilled have more carbon dioxide emissions in this case, for example. And that might be something of interest for us. And you'll see that summarize is written like mutate, new column equals expression. In this case, an expression is a statistical one, right? And I want to clarify with one more example, because I know this can be a little bit hard to wrap your head around right away. So the next example I want to do is I want to use a data set that's also built in, but this time comes with ggplot. I believe if we scroll down, I think it is called MPG. Right there, fuel economy data for 38 models of cars. So if we, since it's built in, we can just run MPG and it should work. There we are. So you have a tibble because it's built in Tidyverse. Different manufacturers, models, displacements, which is a stand-in for engine size. This is in liters. The year of the car, the number of cylinders, transmission type, and so on. And these are fuel economy in city and highway, and this is drive type. So drivetrain, full, front wheel, rear wheel, and four wheel. So in this data set, I want to find the average miles per gallon on the highway, let's say, grouped by the number of cylinders for each engine. So I recommend you pause and try that. So let me write down the instruction. So task, find the average miles per gallon on highway grouped by the number of cylinders for each engine. So I want the average, and report that to me. I'm going to recommend you try this as I'm going to go through the solution right now. So the solution is pretty straightforward. What we're going to do is we're just going to take our data, pipe it into group by, and we're going to group by the variable that I said to group by, which is number of cylinders, which is CYL. And then we're going to do a summarize on it. And in this case, let's say the new column is AVG MPG. The name of the new column is average miles per gallon. And since we're doing an average, the statistic is mean. And we're going to do mean of the highway fuel efficiency, highway miles per gallon. And there we go. For different cylinders, so 4, 5, 6, and 8 cylinder cars, we have our different miles per gallon efficiencies on the highway. And it makes sense that as the cylinders go up, which is generally coincident with larger engines, that our fuel efficiency goes down. And the opposite way around, it makes sense that smaller cylinder cars have a better fuel efficiency. And so that's how we would use grouping. So that's grouping. Feel free to play around with that. There's a lot of built-in data sets. Remember, just run data, look at them, or even play around with bank table and see what we can do there. And actually, maybe as one final example for bank table, I want to show you that we can group on multiple things. So let's try grouping by job and education and seeing how that influences minimum balance in this data set. So in order to do that, the hint here I'll give you is group by column 1 data and then column 1, column 2. And so that'll group by both of those columns, right? So task 2, find the minimum balance grouped by job and education level in bank table. So what I'll do here is like this. Bank table, type it into group by, and remember that this is equivalent to putting the data, the name bank table in here, and then comma, the grouping variable. And so now we want to group by both job and education. And then I want to summarize it to find the minimum balance. So min bal, let's say, is min balance. Run that. And so here for each combination, we see the minimum balance. And I want to be clear what's going on here. We are getting a listing, right, of groups based on unique combinations of both job and education, right? So, for example, for the category of administrative jobs, there's 4 different levels of education that are possible for that, and consequently 4 balances that are associated with that. Same with blue collar. There are 4 different levels of education that are tied to that with different balances. And so we have unique combinations of both the grouping variable of the job type and the education level. And so that can give us a lot more detailed information. So what I'm saying, by the way, is just this. Admin and primary, admin and secondary, admin and tertiary, all the way down to the bottom. That's essentially what this will accomplish for us. So now I think we have a better sense of group by. Let me go into quickly the count function, which, as the name suggests, gives us counts. Specifically counts of unique values of a variable. So clear the console. And this is a dplyr function as well. And we use it to easily count the number of unique values in some variable. It's like a real convenient way of combining group by and summarize, but just with one function. And so, for example, what I mean by that is this. The way we write it is just count and then the variable, the data, the count, and then the variable that we want to list the unique values for. So looking at bank tibble, or even, yeah, bank tibble is a good one. So bank tibble, if we look at it again, we have all this data, and maybe I want to know what are the number of occurrences of each education level. So I could do this, count education. And now for every unique value of that categorical variable education, we see the count. So we see it has 6,800 people with primary education, 23,000 with secondary, 13,000 with tertiary, and 1,800 unknown. We can do other things if we want. For example, we might want to know how many people are how many people have a loan or not. So pass that into count. And 37,000 people don't have a loan or don't qualify for one, and 7,200 do. So maybe this tells us something like the people here have not great credit scores, and that's some information that we might glean from this. We can also count on many variables, not just one. So it's similar to grouping, or in that sense. So, for example, maybe I want to see how many people have a balance less than 0. Or maybe I want to see the different combinations of two categorical variables. So I want to see the different combinations of, did they default and do they have a housing loan? So default, housing. And if we have a look, we got a 4x3 tibble. And so what this shows is the number of times whether a person has a housing loan or not, depending if they've defaulted or not, for each level of defaulting. So for example, here, this, we can read it as they haven't defaulted, they don't have a housing loan. There's 19,000 people that meet that, meet that description, meet both descriptions. Second one is they haven't defaulted and they have a housing loan, and there's more people, which logically makes sense. 24,695 people. The third is they've defaulted and they don't have a housing loan, and there's a couple hundred of that. And the both is they've defaulted and they have a loan, and there's that many of that. And so that's how we can use count. And notice the output is a tibble. So we can assign this if we want to work with it later on. If we wanted to export our final finished work, we can do write CSV, write underscore CSV. And in here, we just put in the data that we want to export, and then the path or the file name that we want to export it to. So as an example, I did all this work to maybe bank tibble, right? So maybe I'll do something, let's do some work to bank tibble. For example, let's filter, select some columns, and then mutate. So again, bank tibble, the original bank tibble, here we are. So we'll do bank tibble, filter, age greater than 18, select age, job, balance, duration, and then mutate. And let's mutate double duration is duration times 2, something silly like that. And we'll call this my fancy tibble, whatever. And so now we've done a filter step, a select step, a mutate step. Okay. So what are we we talking about here? Oh, let's call it ftibble because, you know, whatever. And there's ftibble, and if you have a look at it, there's our new thing. And let's say I'm happy with this. I want to save this to a file. So I'll do write_CSV. We can see, by the way, when we do that, readr function. And then we want to put what we want to save and the path. So we want to save ftibble. And where do we want to save it? Well, remember that our root directory is bank. So I'm going to make a new folder and I'm going to call it output, right? And that's going to go maybe into output, and let's call it my new bank data CSV. Let's see if this works. There we are, new bank data. And now if we go to that location into the bank folder and look at output and look at new bank data and we open it in something like Excel, we get the exact same thing we saw in R, but now in Excel. And that's how we would work with dplyr to do some basic things. So feel free to pause now. I know that's a lot, and I haven't covered everything, but that should be enough to get you going. Our next topic is going to be visualization. So, visualization. And I'm going to be all fancy and do this. So, I'm going to go and just make sure I comment out these lines just so they don't cause issues later on. They shouldn't, but just comment them out as good practice. Feel free to uncomment them out and play around with them later on. So, visualization. Remember that I said we're going to use ggplot for this. But I want to talk to you first that we can do plotting in base R. Obviously, we can. Right? We can plot in base R using a function called plot. And this function, plot, expects a lot of specifically named arguments. Now I'm going to write down some code here using the dataset mtcars, which comes in with base R. You can have a look at mtcars right there. Similar to MPG, but it's built in with base R. I'm going to do a plot here. Don't worry about the code. I just want to demonstrate something to you. And it'll show up, by the way, in the plots tab here. So here's the code I'm going to write. Plot mtcars wt mtcars mpg pch17 cex 2.5 cex main 1.5 family serif ylim c040 color blue, main base R scatter. So let me run this and then we'll have a look. So if we click zoom, we can get a better understanding here. So this is a scatter plot I've made in base R. The point is not really to show you the scatter plot. The point is to show you that we provided a lot of arguments here that don't make a lot of sense if we don't know what they are. What is PCH? What is CEX? What's main? What's ylim? What's family? Right? What do these things mean? Right? They're not very informative. They're not very clear. And it doesn't really make a lot of sense if we don't have the background. And if we want to customize it, let's say, I have these blue triangles, but maybe I want to have blue squares or blue diamonds, or I want my access labels to be different, then I have to use a very specific argument or another function entirely. And that's really limiting approach. ggplot uses a different philosophy. The ggplot philosophy is this. ggplot, and by the way, you can use this to clear all the plots. ggplot's philosophy is something called the grammar of graphics. And by the way, grammar of graphics is where the GG comes from in ggplot. So what is this? It means that we consider a plot as being built of many distinct components. So when I say components, I mean stuff like the title, the x-axis label, the y-axis label, the grid lines, the points themselves, etc. And we say that these components in the grammar of graphics, which we call layers, get laid on top of one another to create the plot. Now that might sound really, really weird, right? And I want to show you what I mean by that. When I run a first plot of just ggplot, I get this blank gray rectangle. So this is just like a canvas that can accept information to plot, but right now it's not showing anything. But then if I add information about my data, like what the x and y axes are, suddenly I get this. I get the x-axis, I get the y-axis, and I get a grid, but I don't have any points showing up. But I've added a new layer of axes and grid lines, so it's better than this. And as the third one, I add points as a new layer and a title. And now we've created our overall plot. And so you can see that we built it in layers. We started with a blank canvas. We added our axes and grid lines. And then we added our points and our title to create our final plot. And that's what I mean when I say it uses a component layering system. And the reason why that's super powerful is this. Each specific layer can be changed in whatever way we desire to produce the specific plot we're after. So what that is saying essentially is that, let's say I like the x and y axes. I like how they're labeled, I like how they're plotted, but I don't want grid lines. I can tackle the grid lines individually and get rid of them. Or maybe I can tackle the title and get rid of it. Or maybe I can worry about a legend and work on that. I can do those individually, and I don't have to change anything else. And because I can individually adjust this, it lets me be more targeted and have way more customization over something like Excel, where this is predefined for you. So to make it more complete, we've already seen that example that I showed you in PowerPoint there, and I hope that philosophy makes sense. We're adding pieces, right? We're adding layers on top of one another to create the overall final plot. And we're going to actually cover in a bit how to make a plot that looks like the one I showed you there. So when it comes to actual plotting, though, when we plot anything in ggplot, we have really just two requirements. The data to plot and the type of plot, which you'll hear referred to as a geometry or a geom for short. And this is how we're going to display the data that we want to plot. And there are a lot of geoms, lots of geometries for all the typical plots. So we have point geom for scatter plots. We have the line geom. We have the bar one, we have a column one, we have a histogram one, we have a box plot one, we have a density one, we have an area one, and so on. There's lots of them depending on what you're plotting, and some of them only make sense for some specific types of data. But there are a lot, and we combine the data with the geometry to create the output that we want. Now, when creating a geometry in ggplot, we need to use something called aesthetics. And what are these? Aesthetic is a function you'll see it written as AES as a function. And what it is, it tells ggplot how variables in our data map to some visual property of the plot. And the visual property itself is called an aesthetic, hence the name. So what do I mean by that? What I mean is it tells ggplot how columns in our data, let's say our tibble, let's say this, it tells ggplot how these columns like cycle, DISP, HP, DRAT, WT, so on. It tells them how they relate to things we see on the plot. So it tells ggplot, hey, what variable should I put on the x-axis? That's defined by an aesthetic. What variable goes on the y-axis? That's also defined by aesthetic. What color should I use for points? That's also an aesthetic. And there's a lots of aesthetics, but generally we use them to create a mapping between some data and a visual property of the plot that we'll see. And the structure that you'll see all over, even in cheat sheets, and I'll pull this up actually, is this. So the structure is, generally speaking, ggplot data mapping equals the aesthetic function x equals variable 1, y equals variable 2, where variables come from our data, plus geometry geom type. That's the general structure of a ggplot function. So ggplot general structure. And that's something that we'll see over and over again, so you become very familiar with it. But here, we provide the data, we do a mapping. So again, this reinforces the fact that an aesthetic is a mapping between a variable and a visual property. We tell ggplot, hey, I want this variable to be the x-axis, this one to be the y-axis, and then I add a geometry to display the points. Now, I want to show you the scatter plot that I did earlier in PowerPoint. This. Let's try recreating it, minus the title and all that. So, first thing I'll do is I'll use this data empty cars. And I'll do this, ggplot data is equal to empty cars. That's the data we're working with. And then mapping equals aesthetic. What I want on the x-axis? Well, if I look, I have weight and MPG. So I want x to be weight and I want y to be MPG. I want to have weight versus MPG. And then, now if I were to run this, what do you think will happen? Well, let's see. So, take a look at this output. We don't get anything points-wise, but we get a grid where the x-axis is weight and the y-axis is miles per gallon. And we see that they have tick marks and we see a grid pattern. So this grid is actually divided or created by the x and y variables. And that comes from specifying the x and y axes variables in our aesthetic call in mapping. And one other thing you'll probably notice when I show the general structure is whenever I want to add a new layer, I use the plus sign. You can think of it as a continuation. It tells R, hey, I want to continue my input and I want to add another layer to this thing. Right now, this is just grid lines. I want to actually show the points. And so let's try just doing this. Geom point for a scatter plot and run that. And wow, look, we got a scatter plot in ggplot. And it's pretty simple. And it works pretty nice. So that's the general structure we're going to follow. And just to reiterate, we have the data. That's what we want to plot. We have the mapping, the aesthetic. That's what variables to display and how to visually show them. And then we have the geom, which is how should the data be displayed. So for example, should it be a point like we just did, or should it be a line, or should it be a box plot, or should it be a histogram, and so on. So that's the general structure we're going to follow. And since one thing to keep in mind here is since mapping with aesthetics controls visual aspects of our plot, it can take on a bunch of other arguments that change how our plot looks like, obviously. So, for example, we can have aesthetics that control the color of our points, or the size of our points, or the shape of our points. So, I'm going to run some code, and then we can discuss it. Twinkle plus geom. So let me run this line. Now, that's not exactly what I want. The reason being, cycle here is not stored the way I would want it to be. So, show you what I mean. Or cylinder, not cycle. That's numeric, but it's a factor. Or it should be a factor. So I can actually do this. I can wrap this in a call to factor, and that should fix everything. And run it again. Okay, there we go. So let's talk about this. What have I done here? First, I've used the pipe operator to take my data and pipe it as the first argument of ggplot, which remember is the data set we want to use. So we just pipe that in, and then we can go immediately into our second argument of aesthetic. And we use the aesthetic function. Here I've said the x-axis variable should be horsepower, which we see here. The y-axis variable should be miles per gallon, which you see here. And then I've used the color aesthetic, which I've set to the different values of cylinder. And you can see we have red, green, and blue points that correspond to these different values of that factor. And we even see a nice little legend that ggplot has provided for us automatically. And then we've drawn it using points, a point layer with plus geom point. And so what we've seen here is the colors of the points are based on the different values of that factor cylinder. So we've mapped a column to a color. That's pretty cool. And it can actually make it clearer for us to understand something. Like, for example, hey, these are the ones that have a smaller cylinder, which means likely a smaller engine, which makes sense why they have such higher fuel efficiencies. This ones over here have a larger number of cylinders, which means a larger engine, which means a lower fuel economy. And so that makes this visually much more understandable thing to see. And we've even seen that it adds a legend. It's smart, and it adds a legend for us. It's not smart enough to title it something nice, but it does add a legend of the different values. And by the way, I want to show you, though, before I did factor on this and I ran it, I got a color ramp, and that's because it was treating this as a numeric. But we know it's a factor. We know it's either 4 or 6 or 8, right, given here. We know it's not something continuous. You know, we don't have a car that has 4.38 cylinders, right? It's either one category or the other. And so we have to represent that as a factor. And doing so gives us the intended plot, like we had earlier. Now, we could also map other values to other aesthetics. Like, for example, there's an aesthetic called alpha, which controls the transparency of points between 0 and 1, where 1 is more opaque and 0 is more transparent. So, let's try this. Let's copy this line. And now, instead of assigning color, let's do alpha. And have a look at what this does for us. So we get an issue that's telling us a warning, don't use alpha for a discrete variable. This is more of a stylistic thing. But you can see here now we get a completely different looking plot where the transparency of the points depends on the different values of that factor. So these ones are very light, they're 4. These ones are medium gray, they're 6. And these dark black ones are 8. And what about changing something like a shape? We can do that. We can change the shape of the points by mapping to the shape aesthetic. And the shape aesthetic, by default, takes some number that indicates the shape, but it can also take a variable. And if we run that, we get 3 different shapes. We get circles for 4 cylinders, triangles for 6, and squares for 8. And so that's some of the different aesthetics we can use. Now, here's a different problem, and I'm just going to comment these out. What if I want every single point to be green? How do I do that? Would I put it into aesthetic? No. Why not? Well, remember what aesthetic is. Aesthetic is a mapping between a variable from our data set to something visual in the plot. If we want something that is invariant, that it's always consistent, like a consistent color that does not depend on a variable, then we have to set it outside of aesthetic. And in particular, we should set it on the specific geometry. So, all that to say, something like this. Color is green. Run that again. And now everything is green, but also different shapes. And it's a little bit hard to see, but we can see that it works as intended. Another thing that might be a little bit weird is expressions can be aesthetics. So, what do I mean by that? So back to what I was saying, expressions can serve as aesthetics. And what that means is that we can provide a conditional expression to be an aesthetic. So an expression like, for example, what I mean by that, just to reinforce, is something like x is less than 3, or x is greater than or equal to 7, or x is equal to a, b, c. Any sort of logical expression like that, we can use it as an aesthetic. So, for example, if we look at the head of empty cars again to get the first few rows, let's say our condition is this. Let's say our condition is if this is less than 250, we want to do an aesthetic based on that. So, let me show you. Empty cars. Pipe that into ggplot. AX, AS aesthetic. X is weight. Y is miles per gallon. And now, geom point. And I'm going to define an aesthetic within geom point here, where the color is equal to displacement less than 250. And let's run that. Well, have a look at what it did here. It gave us 2 colors of points that correspond to a condition. If it's true, we get one color, this light blue, and if it's false, we get another color, this red. And so we can see, for example, that right about here on this line here is where the engine displacement is bigger than 250. And so that's something that we always have the option of using. Now, I want to go back into this shape aesthetic because we did a little bit about it, but not a whole lot. So, shape aesthetic. So, with the shape aesthetic, it lets us change the shape of the points that we'll be using. We've seen that already. And I mentioned it has possible values. It has 25 possible values. And the values that we can provide are numbers like 15 and 8 or 4. So we might say like shape equals 15 or shape equals 4. And each of those numbers means some different type of shape. So let's do a very simple example here of just like a scatter plot of, let's try different variables now. Let's go x is horsepower and y is displacement, whatever. And now I do plus geom point aesthetic shape equals 15. Let's run that. A continuous variable cannot be mapped to a shape aesthetic. Let me pause and double check what this error is referring to. See, I made a bad mistake. I passed something that's not an aesthetic into aesthetic, and it gave me an error. So that's very good of it to give me an error, because this shouldn't be in an aesthetic. This is something that's global, that's true of all points, that has nothing to do with a variable mapping, so it should not be an aesthetic. So it should just be shape by itself. There we are. Perfect. And that's squares, these black squares. And then now, and I did Control Shift D to duplicate. Let's try 18. What shape is that? It's these diamonds by the look of it. They're very small. And final one that I want to look at is shape 4, which gives us these like X's. Now, these are quite small, right? And I think they're a little bit hard to see. So then we can cover the size aesthetic, which lets us change the size of the points that we're showing. And of course, like any aesthetic, we can map it to a variable, although that could get really messy real quick. I just want to show you what happens if we add it to something like this. So size is, let's say, 4. And this is 4 points. A point, I believe, is 1/72 of an inch. So if we run that again, well, now these are bigger and they're more visible. And so maybe that's better for plotting purposes. Maybe it's easier if I put this in a report to see what's going on. And, you know, you can play around with this and make the size even bigger. Let's say like 6. Run that again. And we get much bigger points now. And it's a much easier thing to look at. It's much easier to interpret. So that's something you can play around with. And of course, we can combine aesthetics. So like we can say, you know, we have it having an X and Y axis, but let's say the color is defined by factor of the cycle, the number of cylinders. Run that. And there we are. We get something like this now. We get our custom shapes or a custom size and now colors that correspond to the different values of that factor. And so this is what I say about ggplot being powerful. We can just add on to and customize what we need and leave what we don't alone. And so we have very, very, very granular control over what we do. Now, one thing I want to mention before we go on any further is we can bind a plot to a variable. And that's something you'll see a lot. Like you'll see like base plot is something like this. ggplot. We can map it to, I don't know, ggplot, AES, aesthetic. We can do this. And then now, when I run this, I'll have a plot. If I look at it, if I plot it, it'll come out as a plot with nothing on it. And then I can simply add on to this. I can do base plot plus geom point. And there we go. So that's something you might see as well. So assigning. That's something that is pretty common. Reason being, it just makes everything a little bit more readable because it breaks up the code into little tiny bits. Now, there is something maybe that you've noticed here. If I provide an aesthetic mapping in the main ggplot function, so in the call to ggplot here, all subsequent geometries use that mapping by default. So geom_point used x being horsepower and y being displacement. It used that by default. It didn't ask me what is x and y. It used that, it got that and inherited that from ggplot. Similarly here, in this last line, it took all the x and y and the color variables and drew them as points. But what's interesting to note is that if we have aesthetics defined in a specific geometry, they only apply to that geometry. And so we can have, in this case, we don't have an aesthetic for size or shape, but we do here. What it also means is we have two aesthetics for color, one in the ggplot function, one in the specific geom function. The one in the geom function can overwrite it. So, an example, overwriting aesthetic. So, an example might be, we have base plot, yeah? Base plot defines an x and y, but not exactly what I want. So what I want is more like this. Y equals displacement, color equals, and I don't really remember what empty cars looks like, so let me very quickly pull out the head of empty cars. Right. So color, let's say, is defined by factor of AM, which I believe is the type of transmission, automatic or manual. And then now let's go geom_point and set a different aesthetic for color to be factor cylinder. And let's run this. Now, this is a little bit weird, right? But the title here says it's factor for transmission, but the values are for cylinder. We obtain the color in the specific geometry point here of 4, 6, and 8, which correspond to the different levels of cylinder. We do not have the colors for 0 and 1 like we might expect here. And so that means that we've overwritten an existing aesthetic of color with a more specific aesthetic in that call to the geometry function. That's not something that you'll do terribly often, but you might encounter it. So I just want to make you aware that that's something that could happen. And just something to keep in mind. We can also have multiple geometries on the same plot. So multiple geoms on same plot. As an example, I'm going to use the geom_point that we've been using so far and geom_line for a line plot. So let's do this. Base plot. I'll redefine it. Base plot is already defined in my environment, right? So if I go base plot plus geom_point plus geom_line, then we get some points, and then we have them connected by lines. Now, let me be more precise about this. We're drawing in layers. So that means we draw the points first, and then we draw the lines on top of them, and they're connecting the points to create this abstract shape. What do you think would happen if I did this? Would it look the same or different? Let's have a look. It looks pretty similar. But what we're doing here first is drawing the line first and then adding the points later. And so that might give us points where we otherwise wouldn't see them before, that they might be overlapping with the line. And so we have both a point geometry and a line geometry on the exact same plot. And notice that we would use a plus to indicate that we have separate layers. We have our base layer, an additional layer of points, and an additional layer for the line. So that's something we can do quite a bit, and we might see it in cases like we might see it if we want to have multiple types of geometries on a single plot to illustrate something. Obviously, we can plot categorical variables too, variables that have a specific number of values. We can do it with things like bar charts or column charts. And for bar charts, the geometry type is geombar. For column charts, it's geomcol. So, say bar and column charts. So, let's have a look at our data for empty cars again. If we look at it, we have some category variables like the number of cylinders, the transmission type, whatever VS is, the gear, things like that. And we can use a bar to plot it. Now, let's try it like this. Let's actually do it ggplot data equals empty cars, static. Now, x equals am. Now, have a look at this. Does this match what you thought it would match? We just provided an X aesthetic. So where does the height come from? Right? Why do we have a bar? Where does that come from? Well, what's happening here is by default, geombar uses count on the y-axis. We can actually see that right here, count, without us specifying that behavior. And what that means is it counts the number of cases for each value on the x-axis and plots that on the y-axis. So, for example, we can see there's maybe like 17 cases of this am variable being 0, and let's say like 14 of it being 1. And remember that we can use dplyr's count to find this, because we are plotting count. So we can do something like this. Count am. And this should give us the exact values that were being plotted. So this is what's being plotted. We're plotting 19 for this column, 13 for this column. Now, maybe another thing you might have spotted is I said color red, but the bars are gray. What's going on? But the outline is red. Maybe you haven't noticed that, but the outline is red. So the red is being applied, but not to the bar, or not to the inside of the bar. And why is that? Well, when we're dealing with something like a bar that has like a width to it, an area to it, if we want to change what the inside color looks like, we don't use the color property, we use the fill property. The color property lets us adjust the border color. So let me show you. If I change this from color to fill and run it again, there we go, our red bars, just as we might want to expect them to be. And we can, of course, do both. We could have color be black and fill be white. We get something like that, right? Where the border is black, but the fill is white. And so that might be a nice, minimalist way of showing this data. And like I said, color just changes the border color. But here we just have count as the y-axis. And the other thing, and this is, if you didn't notice this, perfectly fine. This is continuous, this axis right now. But we know AM is only 0 or 1. Right. There is no transmission for half, and these numbers are not numeric. They're categorical. They refer to different types of transmissions, right? Manual, automatic, or automatic manual. I'm not sure which is which, but they're a category. They're not numeric. So what's the issue? Well, it's being treated as numeric, right? If we look at empty cars AM in our console, numeric, right? And again, remember structure is your friend here, or even summarize, or summary, I believe it is. Empty cars. Yep. So if we have a look, AM, yeah, it's being treated as numeric because it's trying to compute quantiles and median and mean for it, but it's not. It's categorical. So what I can do is just wrap it in a call to factor like we did for cylinder and run it again. And now we get exactly what we should get. 0 and 1. 2 different categories and bars for each. And everything works as intended. Now, let me make a note of this. By default, y-axis is count for each value on the x-axis. And that might be good for a lot of purposes. But then what if I wanted the y-axis to be an actual value rather than a count? Right? What if I don't want the y-axis to be the number of something, but an actual other value? And the way we do that is through the geom call geom. That's designed for that because geom call takes x and y aesthetics. So geom call takes both x and y aesthetics, meaning that it can plot the actual values of x versus y, where x is categorical and y is numeric, rather than just a count. So what's a good use case for this? Well, we could play around with dplyr in our existing data to do this. So let's go back to group by and summarize in this particular case. So remember that in dplyr we have group by and summarize, and this will produce a new tibble as an output, right? And so what I can do is I can assign this to a variable. So I'm going to create a variable called CILDF, and you'll see what I'm going to do with this in a second. But we'll go empty cars, pipe it into group by from dplyr, dplyr. We're going to group by cylinder, and then we're going to summarize, because now we have groups for the possible values of cylinder 4, 6, and 8. We're going to summarize the total horsepower as being the sum of the horsepower column for each. And I'm going to show you. We have a look at this. Here's our 3x2 tibble. Columns are what we group by, and then the summary column. All right. So for 4, 6, and 8 cylinder cars, these are the total for the horsepower column for each. And so now, what I can do is I can plot this, where these would be my x values, 4, 6, and 8, and these would be my y values, the horsepower. So ggplot CYLDF. Mapping for the aesthetic. X is the factor of CYL. Factor because it's being already stored as a double here, which I don't love. And then Y is equal to total HP, or horsepower. And geom call. Now let's have a look. Error occurred in the first layer. Did I add? Yeah, I think I added too many columns. Or too many. I think I added too many brackets. Yeah, there we go. So now we have a column plot. It looks like a bar plot, but now look at our axes, right? And let me zoom in because this might be a little hard to see. But on the x-axis, we have factor and 4, 6, and 8 for the cylinder values. But on the y-axis, we don't have count anymore. We have the actual value of the y aesthetic total horsepower. And we can see that this one's about 9,000, this one's about 8,000, and this one's around like 2,800. Sorry, 900, 800, 2,800. And that's a column plot. Now, I'm going to show you a little quick trick here. When we think about columns, we usually think about them as being, running horizontally, not, vertically up. Quick trick here is running using this chord flip. I'm going to flip the X and Y axes. So it's going to put 4, 6, and 8 here. It's going to put horsepower here. Watch what this does. And that looks like a column chart more, doesn't it? So now we have horsepower, total horsepower here, our summary statistic on the X, and our Y value, our X value on the Y, and our Y value on the X. And so now we have horizontally laid out bars, and that might make it easier for us to compare the different categories. Of course, now I'm thinking this doesn't look aesthetically too amazing. We could set the fill to be a variable, right? But we only have cycle and total horsepower. So we don't have a variable we can really set it to, but let's set the fill to, I don't know, purple. Whatever. It's just something that's not gray, right? And there we go. Something a little bit more aesthetically nice to look at. So that's a nice little way of getting both bar charts and column charts. Now, let's talk about stacked bar charts. So, stacked bar charts, I'm sure you've seen them. They're the bar charts where you have one bar where you have one part is one color, then another part is another color, and the third part's the third color, and they show you proportions of a particular quantity, right? The easiest way to make them is we start with the same way we would make a bar chart, but then we specify a fill color based on a variable. So I'm going to plot something here, and then we will talk about it. So the data is empty cars, and we don't even have to put in data. We can just put empty cars. Static x equals factor of the transmission type. And then fill equals factor this plus geom bar. Okay, let's run that. And I get my stacked bar chart. So what's going on here? How did this work? Well, we know from earlier that our transmission type has two values, and we converted it to a factor in order to just have 0 and 1 instead of a continuous range, which is what it's stored as. Each bar, so we have two bars, each of those bars is filled with a color which corresponds to the different levels of cylinders in that class. So, for example, each bar will be, what that means is each bar is divided into pieces for each type of cylinder. So a 4-piece, a 6-piece, an 8-piece, giving us this stacked appearance. Now, there's a problem with this. And these are counts, by the way. So we can see like the most in this category, the most are 8 cylinders, and this one the most are 4. So you might say that these ones are whatever transmission type is. This is more for smaller cars, and this is for larger ones. The issue is we have different bar heights, and that makes it very difficult to compare proportions. And there's a quick fix for that. We pass another argument called position fill. Position equals fill to geom bar. And what position fill will do is it will create bars which represent the proportion of each of those categories. So each of the cylinder categories. And it'll make the height of each bar equal 1 for 100%, which will show the relative proportions of those cylinders between the two groups. So all that fancy schmancy talk to say this. Right. So now this is misleading. This is not a count anymore. See how it's 1.75.5? These are proportions, like 25%, 50%, 75%. And now we can see, well, this one is about 60%, right? 62%. This one's about whatever. This one's about maybe 20%, where this one is maybe more around like 60%. And we can actually compare that now much more easily. And that's the whole point of doing something like this. Now, the colors that we've been doing here have been automatically assigned by ggplot, right? This light red, this green, this blue. I haven't done that. It's done that automatically for me. But let's say I have my own colors in mind that I want to use, that I think look good for my purpose. We can actually manually adjust the fill colors for the bars. Or even use color palettes if we are so inclined. But I want to show you the manual approach because it gives me the most customization. To manually adjust the fill colors, we use a function called scale fill manual and the values for that. It's a new layer because we're adjusting the color of the plot. And because it's a new layer, we would add it with the plus, right? So let me first show you that there's two ways to work with it. We can provide named colors or color codes in a system called hexadecimal. So for named colors, I'm going to pull up this website. These are the names of different colors that are built into ggplot. If you provide this name, ggplot will draw the corresponding color. For example, if I provide green, it'll draw this shade of green. If I provide deep pink 1, it'll draw this. If I provide chocolate, it'll draw this brownish hue. If I provide orchid 4, it'll draw this darker purple. So let me show you color palettes here very quickly. Manual color palettes. Manual colors. So first thing I'm going to do is I'm going to create a character vector of the colors I want to use by their name. So block colors is going to be a character vector. And I'm going to use the colors Orchid 4. And notice that RStudio is going to show me what these colors look like, which is nice. Orchid 4, Forest Green, and Royal Blue 4. And I'm getting these from this website. So these are the colors that I want to use. Right now, these are just characters. They don't mean much. But when we combine them with our existing plot, we will get something that looks different. So we'll do a plus here, and I'll move to the next line because it's going to be cramped otherwise. And I do scale fill manual. And now I say values equal plot colors. So we use the scale fill manual. We use fill because we want to adjust the fill. We use manual because we want to adjust the manual values to equal to the character vector we made. And the reason I'm using 3 values is because we have 3 values, 3 unique values for the cylinders, 4, 6, and 8 on that. And now we get different colors. We get our orchid, we get our forest green, and we get a royal blue. And, you know, you could argue that this looks worse or better. I think that's a fair point to make. But the point is that we've customized what the exact colors are that ggplot is showing to us. And so if I really liked Orchid 4, I could use this. But there is a limitation here, right? We have to know the name. And maybe the name is not exactly the color you want. Maybe we want something that is a little bit more red, or a little bit more green, or a little less blue. And so the way that we handle that is, like I mentioned, with hexadecimal colors. Now, won't get into too deep with this, but hexadecimal. This is a system of writing numbers, and we have codes. And the way we write them is an ampersand, or pound, sorry, RRGGBB. So 2 values indicate the amount of red, 2 values indicate the amount of green, and the last 2 values indicate the amount of blue. So, for example, 0, 0, 0, 0, 0, 0 means every color is 0. So no red, no green, no blue. And you can probably predict that that's going to make black, as an example. And what I want to do now is with the system, I'm going to use some hexadecimal colors. Now, you can find these colors if you go online and just search for hex color picker. You can just look around and find whatever you want and then copy it here, and that's the hex code we're going to use. So I did a similar process here. The hex codes I want to use now for new plot colors are 666 FAB, and RStudio will actually display this for us so we can see what they'll look like. BB2649 and 88B04B, or yeah, 4B. Yeah. So there's our new plot colors. And now I'm just going to run this exact same line, but I'm going to specify the plot colors as being, instead of plot colors, new plot colors. And have a look at this. Now we get those exact hex colors that I provided. This sort of olive color, this darkish magenta, and this nice soft lavender purple. And so you can play around with this as much as you want. And if you want to play around with color palettes, I recommend searching Scale Fill Brewer and also Scale Color Brewer. There's a lot of palettes that you can use that are predefined in order to create different sort of effects if you don't want to use specific manual colors. So that covers colors. Now, labels. So labels, what do I mean by labels? I mean stuff like titles and captions, subtitles, x-axis label, and y-axis label, right? Because right now we have factor AM and count. That doesn't really, and with no title. So if I gave this to you and I didn't tell you anything else, you would have no idea what this means. Right? There's no way to tell what this data is, what it's showing, what the variables mean. Not only that, that's misleading. It's not count, it's a proportion. So you'd be completely wrong in your interpretation. So let's fix that with labels. And the way we fix that in ggplot is the labs function, short for labels. And this function takes very self-explanatory arguments, I believe. So, for example, you want to change the title. You set title equals whatever. Or I want to change the caption. Caption equals whatever. Oh, I want to change what the x-axis is. Okay, x equals. Oh, what about the y-axis? Y equals. Very simple. But this is a new layer. It's a separate layer. So what that means, again, remember, separate layer. So use that. Now, I'm going to keep it nice and simple. And let's take a look at our plot from last time here. And now I'm going to add a title to it. So, labs. Okay. And you know what? I'll put it on a new line because I'm going to run out of space pretty quickly. So, title equals proportion of transmission, proportion of automatic, manual, transmission cars by cylinder size. Caption, which will show up in the bottom of the figure down here, is going to say data from MT cars data set. The x-axis title, we don't want it to be factor in AM anymore. We could say it's transmission type. And the y-axis, we don't want it to be count. We can say proportion. And now, if I run that again, there we are. We have our title that we specified. We have proportion on the y-axis now. We have transmission type on the x. And we have our little caption that shows where the data comes from. So now I can understand how to interpret this and make sense of it. It's looking a lot more like an actual presentable plot, in my opinion. You will notice, though, this is not centered. That's something you can adjust. And also, the legend is still factor bracket CYL, which, doesn't really scream anything useful, right? Quickly, though, I want to cover themes. So, labeling example. So, I want to cover themes quickly. Not a big topic. ggplot comes with some built-in themes that let us customize like the background color of the plot, whether there's grid lines or not, what the legend looks like, its size, things like that, whether it's dark or not. These are a separate layer, so of course we have to add them. Now, I'm going to make things easier. Now look at base plot again. It's nice. It's just like an XY axis with nothing on it. We have horsepower versus displacement. Let's add a geom point to it. Let's have a look. Perfect. And make it a little bit bigger. Why not? Right? And then now I'm going to add theme_classic. And notice how that transformed everything to have now no longer this grayish background and these grid lines, and just have nice tick marks and a nice clean XY axis. So there's other themes, obviously. We can do stuff like theme minimal, where that creates this without the axes. So that could be something that you might find useful. And one more, just for good measure, I believe is theme dark, which plots everything in a sort of darker shade, which might be something that you like to see. Won't go too deep into this because it's kind of like whatever, right? It's not as important. Now let's talk about legend customization quickly. And for this, we use a function called guides to customize legend. So this function, I'll show you what it really expects is an aesthetic, and then how that affects the, and then another function to change to say how that aesthetic affects the legend. So as an example, the fill aesthetic, if we wanted to change the title, so change the title, we'd use something like guide legend and then title equals whatever, right? But we'd have to use that in respect to an aesthetic, right? For example, above here, we're filling by cylinder, right? And remember, if I just do this, if I just do the simplest plot I can, and not worry about all these other things. Remember here that our legend is defined title by their fill, right? And so we have to give this in respect to, when we modify the title, you have to be in respect to that aesthetic that the legend is based off of. In this case, it's fill. So we would say something like guides fill equals guide legend title equals something. And what that is telling ggplot is, for the fill aesthetic, customize the legend title to be whatever I specify. So, as an example, guides for the fill aesthetic, the legend title, which is this, will now be number of cylinders. If I run that, there we go. Number of cylinders, exactly like we might expect. So for this fill aesthetic, which is what our legend was based off of, we used the guide legend function to change the title property to something more useful. If we combine that with what we did previously, we have a nice looking plot. Now, one final thing to mention, one big topic, faceting. And I'll argue that this might be pretty complicated to understand initially. So let me be gentle with how I introduce this. And I'll push it down a little bit just so we have a nice clean workspace. So often, rather than having some large plot, we typically want to have a bunch of smaller plots that show us how some categorical variable influences the relationship between some existing values. So what I mean by that, simply put, I want to see what relation some third categorical variable, like maybe marital status, or the quality, or the type of car, the class. Is it a compact car? Is it an SUV? Whatever. What relationship that would have to some relationship like fuel economy. And in order to do that, in order to have separate individual plots or subplots for every value of that variable to tease out visually this relationship, we have to do faceting. And let me give you an example just to make this clear, because I know it's a little bit hard to understand right away. Suppose we want to compare fuel economy in the city, which we know in empty cars is CTY, by car class to see if some types of cars are more fuel efficient than others, and also which types those are. So that is a classic use case for faceting. And to think about a facet is basically one variable. We could have more, but let's say one. We use to split our plot by into subplots based on that variable's unique values. And because it's unique values, it's usually a categorical variable. If you try to do it on a continuous one, R is going to complain. You're going to have a million plots. Right? It's another layer. So our friend plus sign is going to come back in because it's a new layer. And I want to show you an example. First, with a function, I'm going to show you it through the lens of a function called facet rep. So this is a function which takes a formula that tells ggplot how to facet by. And when I say formula, I mean something like this, bar, where you can read this as being the same thing as facet according to variable. So, example, right? I think an example will clarify everything. So, empty cars. We have our data, And I don't love it, but let me do another data set called MPG. MPG comes, it's a table, it comes with Tidyverse. And we have a column called class. And let me very quickly just do this. Count class. So we have all those different classes there. Two-seater, compact, mid-size, minivan, pickup, subcompact, and SUV. And so let's say I want to facet on that. And I want to look at the relationship between engine size and city fuel economy, faceted by class. So faceted according to class. How do I do that? Well, the way we would do that is we'd write this. MPG, which is our data set, pipe it into ggplot. We'll define some aesthetics. We'll say the x-axis is the display variable. And I always recommend doing a view before we do this. So we see what variable. This is displacement, not display. So we go by displacement on the x-axis. And on the y-axis, we do CTY, stands for city fuel economy, or city miles per gallon. Okay. Then we're going to add a geom point. I'm going to make the color equal to the drivetrain, let's say. So factor DRV. And we'll make the size equal to 5 just to make it a little bit bigger. So that so far is nothing new. And actually, what I'm going to do is I'm going to assign this to a variable. Let's say P1 for plot 1. This is not a great naming convention, but object DRV not found. Pretty sure it is. Why might that be an issue? What's going on here? Let's try MPG DRV. That works just as intended. Why might that be an issue? Well, let's have a look at glimpse MPG. This character should work. I wonder, could it be related to how I defined my, looks fine to me. Object DRV not found. Let me pause and fix this error. Forgot about aesthetic. This is an aesthetic because we're associating color. We're mapping the variable DRV, its unique values, to the color aesthetic. This should work now. So look at P1. There's our different values of DRV, our factor, by color. Points are a little bit big, so I'm just going to make it smaller. Yeah, I like that a little bit better. That's a little bit better looking. So we have our color defined by our different drivetrains. We have our displacement on the x-axis, our city miles per gallon on the y. So far, nothing new. Now we add the facet wrap. And the formula is tilde, which is shift, and then the key beside 1, class. And when we run this, we get this interesting output. We get this really interesting looking output, right? We get a bunch of subplots, right? 7 in total, right? 1, 2, 3, 4, 5, 6, 7. And notice that they flow onto the next row. So we have 1, 2, 3, and then it goes back around to 4. It wraps onto the next row. That's why it's called facet wrap. This is not actually a grid, but it just wraps rows of plots, of subplots. And we have 7 subplots, 1 for each value of our class. Two-seater, compact, mid-size, minivan, pickup, subcompact, and SUV. You can actually see that back here. compact, if we scroll up a little bit. Believe I did it, or yeah, I did it earlier, where you can see these are the values that we have. And what each plot is showing is the relationship between engine displacement, which we use as a proxy for size, and highway and city fuel economy in miles per gallon on the y-axis. So the x-axis is displacement, which is a stand-in for size, and the y-axis is miles per gallon in the city. And it shows that relationship for each particular set of vehicles. And we can see right away there are no two-seaters that are four-wheel drive or front-wheel drive. So that might be interesting. We can see there are no mid-size that are rear-wheel drive. We see their pickups are all four-wheel drive. We see our minivans are all front-wheel drive. And so that's something to be interesting. Maybe it's interesting for us to notice that, but it also shows the relationship here, and it doesn't really look super clear for some of the variables, but it looks clearer for others. Like for pickups, it looks pretty clear. For subcompacts, it looks pretty clear. For SUVs, it looks roughly linear. And so it lets us visually compare things. We can see, for example, the pickups have larger engines in general, right? And they have poor fuel efficiency, while compacts up here for displacement are generally lower to the left, and they have smaller engines in general and better fuel efficiency. So it allows us to visually compare a lot of categories very quickly. And that's the whole point of using facets. Really, just to summarize, facets are used to provide a visual way of comparing trends across different categories easily. That's the main point of facets. One final thing I will tell you, and this might be confusing. We can facet on more than one thing. Because facet wrap defines a formula, we can add other variables to facet by. The way we do that is we write, facet wrap variable 1 plus sign variable 2, and that means facet on both that and that. So let's try, for example, in this case, P1, our data for MPG. What can we facet by two ways? We already faceted by class, but what if we facet by class and model maybe? Well, let's see how many models do I have? Probably a lot. Probably not a great choice to facet on. Not that many, 10. So let's do that. Let's try that. MPG, we already have P1. Let's do a facet wrap class plus model. Now, this output is going to look really strange. And it might take a minute to load because we have to draw a lot of subplots. Yeah. So here's what we get when running facet wrap that way. So what do we see here? We see facet plots for each combination of the two variables that we faceted by. So we have essentially a grid of plots that corresponds to each unique combination of the two. So compact two-seater Corvette, compact A4 Quattro, compact Altima, compact. So these are all compacts up here, and these are models for the different models. And we can see we have a bunch of plots, right? SUV, Land Cruiser Wagon, SUV Mountaineer, four-wheel drive, SUV Navigator, SUV Pathfinder, SUV Range Rover, subcompact Mustang, subcompact New Beetle, subcompact Tiburon, and so on. So this lets us have really, really finite control. We can actually see a bunch of plots. And actually, the number of plots that we get is the number of categories in each one of these multiplied together. So we have 10 categories for count for model, and we had, if I remember right, before 7 categories for our class. So what that means overall is we have 70 plots here, right? And we can just look at this: 1, 2, 3, 4, 5, 6 by 7. So 6 times 7, and we don't really have full 7, really. It's more like 6 times 5 and then added a couple more. But we should have 70 here, right? If I'm thinking about this right. Because, let me just verify, MPG class, and we'll use the unique function here because I'm feeling a bit lazy. Yeah, so we have 1, 2, 3, 4, 5, 6, 7 values, and then we have unique MPG model. Yeah, and we have actually way more than we're showing here. We have 38. So we should have more plots than we're actually able to display here. But we can see that that's something we could do if we really want to. Usually I don't recommend doing this. It gets really messy, as you can see, and it doesn't really give you a whole lot of extra information, especially not on this data set, but it could be used in some cases. And of course, I'll make a note, we can facet wrap on categorical variables as well. And that's something you can play around with. The final thing is ggSave. This is what we use to save our plots. So I'm going to have my plot P1 from earlier, okay? And I want to save that. So we're going to write ggSave. Then we're going to put in the file name that we want to save it to. So, and in this case, it's going to default to my working directory, which we have here. So let's call this facet wrap mpg.png, let's say. The plot save is P1. And then we can add things like the width, which is in inches. So let's go 16. Height is 9. So 16 by 9. And then DPI, which is how high the quality is. Let's say 300. Run that. And another way, we can also do export here and click on image or save as image or save as PDF. And now if we go back to bank, should see facet wrap here. And if we click on it, boom, there's our facet wrap picture, just as we defined it in R. And we can use this in our reports and do a lot with it. So this video has been going on for a long time. I appreciate you if you've been listening so far. Feel free to skip around. But I hope this provides you with a good understanding of the Tidyverse and how to work with things like filtering, how to use dplyr, how to use ggplot, and how you might approach assignment RA1. In the next video, I'm going to do a very brief video where I give you some intuition for how you might approach RA1. It's more open-ended, so you have a lot more options. Once again, thank you for watching, and see you in the next video.